Hello everyone, welcome to our video on vector multiplication. So there are three ways to multiply vectors. We'll be talking about each of them. The first is when you multiply a vector times a scalar. And the next two are multiplication between two vectors, the dot product and the cross product. Alright, so we'll start with a pretty simple one, the scalar multiplied times a vector. Well, it probably works the way you think it would work. Let's say you have a scalar, and we'll call it alpha, and you have a vector v, and you multiply the alpha times v. Well, it's kind of like it just distributes. We know v is equivalent to vx times unit vector I plus vy times unit vector j, and if it's a three-dimensional vector, it'd be vz times unit vector k. So when you multiply a scalar times a vector, the scalar multiplies by each component. You get alpha times vx, alpha times vy, and alpha times vz. So this makes sense if you think about it. Let's say you had a vector that told you were going to walk 2 miles to the northeast, right? And then I said, go ahead and walk twice as far, right? You would walk in the same direction, and you would walk a little bit further north, and you would walk a little bit further east in the same proportions that you did before, right? So you multiply each component of your vector, you would double each component of your vector. All right, so that makes sense. So the next product we'll be dealing with is called the dot product. And it's a way that you multiply two vectors and you turn it into a scalar. So two vectors becoming a scalar. So that's interesting. So the dot product definition is a dot b. So a dot b, we have two different vectors, is going to be equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. All right? So that's interesting. So this cosine, okay, cosine of theta, what do we know about cosine? Cosine, if theta is 0, would be 1. All right, so let's think about this example as applied to unit vectors. Okay, if we had the unit vector I, and you want to know what is the dot product of the unit vector I with the unit vector I. All right, so we know it's going to be the magnitude of I, which is 1, times the magnitude of I, which is 1, times the cosine of 0, which is 1. So overall, that's going to equal 1. Right? And you could do the same thing with j. The dot product of j times j, j dot j, magnitude of j, which is 1, times the magnitude of j, which is 1, times the cosine of the angle between them. Well, there is no angle between them because they're pointing in the same direction, equals 1. So that equals 1. Well, what about I dot j, right? So now we're going to be dealing with I is going in this direction and j is going in this direction. So what is the dot product of these guys? Well, they're separated by an angle of 90 degrees. All right, so we have the magnitude of I, which is 1, times the magnitude of j, which is 1, but then it's times cosine 90 degrees, which is 0. So 0 times 1, 0. So the dot product of perpendicular vectors is 0, and the dot product of parallel vectors is kind of just the square of the multiplication of the magnitude of those vectors. So similarly, I dot k would also be 0 if we're dealing in the 3 dimensions, because I and k are also perpendicular. So another way to define the dot product is kind of if you write out the vectors in their component form, right? AX times I, AY times unit vector J. And then same here, BX times unit vector I. And what you can do is, right, we have 3 components over here times 3 components over here. And if you distribute these, right, AX times this guy, AX times this guy, AX times that guy. I always think when we're distributing components, it's kind of like Battleship. They're kind of like firing at each other. Anyways, 3 components on the left side times 3 components on the right side means we're going to get 9 components. We're going to have AX times BX, and they both have I dot I, and then the magnitude AX times BY times I dot J, and let's say the magnitude AX times BZ, so we're just thinking about this guy multiplying by these 3 guys. And what you'll notice is you have I dot I, that's going to be 1, right? As we just set up here. I dot J is multiplied by this term. We just said that's 0. And I dot K is also 0. So these 2 terms are going to go away. J dot I is also going to go away. Those are perpendicular. J dot J is going to stick around. J dot K is going to go away. This will go away. This will go away. So this reduces to 3 terms, which makes it pretty easy. So we have AX times BX plus AY times BY plus AZ times BZ. And notice that this is a scalar. It's not a vector anymore. We kind of have, I just gave you kind of 2 different definitions of the dot product. The magnitude of A times the magnitude of B times the cosine between them, and this component form. And they're actually equivalent, and you can prove that without too much trouble. We're not going to do that here. But when you set those 2 different definitions equal to each other, you can also solve for the cosine, right? So if someone gives you the components of a vector, of 2 different vectors, you can use this definition of the angle between them to solve for the angle between them. Cosine of the angle between the vectors is going to be equal to AX times BX plus AY times BY plus AZ times BZ over the magnitude of A times the magnitude of B. All right, so quick thing to note about dot products. A couple of rules apply. A dot B is equal to B dot A, so you can reverse the order and it stays equivalent. And it distributes. If you do the dot product of A dot B plus C, that's, this distributes through, and you can have, that's equal to A dot B plus A dot C. All right, now we're going to move on to talking about the cross product. Sometimes this is called a vector product because the cross product is when you multiply 2 vectors and it creates another vector, a single vector. So it's unlike the dot product, which creates a scalar product. So first we're just going to talk about what is the magnitude of the cross product. Remember, when we talk about magnitude of vectors, we use that little absolute value sign. So the magnitude of the cross product, A cross B, is equal to the magnitude of A times the magnitude of B times sine theta of the angle between them. Now the direction that that vector is pointing, it comes from the right-hand rule. So the right-hand rule says if vector A, the vector out in front, you kind of point your index finger in the direction of A, you curl your fingers, or curl your middle finger towards the direction of B, and then your thumb pointing up is going to be pointing in the direction of A cross B. And so you can kind of imagine A and B are kind of creating a plane, right? When you have 2 lines, they can create a plane, and A cross B is always going to be perpendicular to that plane. right? It's moving. If you A cross B, or if A and B vectors are creating like a page, like a sheet of paper, A cross B, that vector would be pointing straight out of that page. All right, so let's think about the cross product of some unit vectors. All right, so I cross I, right? The magnitude of I is 1 times the magnitude of I is 1, and now we multiply it by the sine of the angle between them, which is 0. Now it's the sine, so the sine of 0 is 0. So this is saying that the cross product of completely parallel vectors that are going in the same direction is going to be 0. Okay, so that's interesting to note. Similarly, j cross j is going to equal 0, and k cross k is going to equal 0. What about perpendicular components? Well, the magnitude of perpendicular components, like unit vector I cross unit vector j, that'll be 1 times sine of 90 degrees, which is 1. All right, and similarly, I cross k is going to be equal to 1, and j cross k is going to be equal to 1. So what about their direction? That was their magnitudes. So I cross j is going to be equal to positive k. But something interesting about the cross product compared to the dot product, if you reverse the order, j cross I is going to be actually equal to negative k. It's going to be, right? Remember, our unit vectors, I is kind of horizontal here, j is moving up, and k is kind of moving into the page. J cross I would be moving the opposite direction out of the page. So that's interesting. And you can kind of think of it this way, right? We're using that same right-hand rule, and you start with pointing your index finger on the vector that is listed first, right? So if we were to do, if this is I and this is j, looking down at here, we start at I, point our index finger in the I direction, and how many degrees does it take to rotate counterclockwise until we get to j? It would be 90 degrees, right? So sine of 90 degrees equals 1, right? If we think about a sine wave, right? Sine of 90 degrees is 1. But what if you start at j and you rotate counterclockwise until you get back to positive I? Well, it's going to take 270 degrees to do that, and the sine of 270 degrees is negative 1. So that's kind of why j cross I is pointing in the negative k direction. Okay, so you can show similar things with I cross k versus k cross I. When you switch the direction, and when you switch the order, the direction reverses. Okay, so similar to how we talked about with the dot product, we can think about writing out the components of each vector and then distributing those components, right? So we'll have AXI plus AYJ plus AZK multiplied by BXI plus BYJ plus BZK. And if you multiply and distribute those terms, you're going to have 9 terms again. But let's kind of simplify this. So before we talked about, let's distribute this one. What would happen? AX I times BXI, that's going to equal 0, right? And if we do AXI times BYJ, that will be positive. But then if we did AJY cross BXI, that'll be negative. So anyways, you could distribute all of these terms, and in the end, what you're going to get when you simplify is this. A cross B is equal to AY times BZ minus AZ times BY times unit vector I, and then AZBX minus AXBZ times J plus AXBY minus AYBX times unit vector K. All right, so some cross product rules. So this makes it different than the dot product. A cross B does not equal B cross A. A cross B equals negative B cross A. So that kind of makes sense before for when we talked about how, I cross J equals positive K, but J cross I equals negative K. All right, but similar to the dot product, it also distributes. So A cross B plus C is equal to A cross B plus A cross C. All right, so that's going to do it for cross products. So you might not see these showing up, the cross products, in the next couple of weeks, but it is going to come super, super in handy after we start talking about torques and rotation and later on in the semester. So, try and understand these concepts now so that when they come back later, you will be prepared. All right, thanks everyone, and have a good day.